we're going to continue with other numerical methods. We've discussed the midpoint rule, which is pretty accurate actually. If you're curious, one of the reasons you use the midpoint rule is because it's guaranteed to be more accurate than the left or the right on its own. Does that make sense? So we started with the left or the right because you can take the limit of it and you get the definite integral. But if you don't want to take the limit of it, basically, if you don't want to take the limit of your Riemann sum, it makes more sense to do the midpoint, especially for low values of n. Like basically, because like you can imagine if you have this sort of curve, the middle, if you do the midpoint, some of it will be under and some of it will be over, and they balance each other out most of the time. And yeah. And interestingly enough, like unless the function is like super curvy, it basically is going to be is going to be pretty accurate. Now there are more accurate methods, is the cool thing, and that's what we're going to talk about now. We're going to use trapezoids as our shapes. So let me go to the writing. Okay, wrong thing. Crap. Okay, there we go. Jeez. I'm like, where did it go? Sometimes the struggle is really real about trying to get the damn thing on the screen properly. I was like, where did it go? I was like literally like dying inside. Okay, so let me sort of draw what's going on with the trapezoid rule. So you've got this function. There's your f of x. And there's your a. There's your b. And let's draw 1, 2. There we go. Good enough. Okay, so you have x0, x1, x2, x3. And actually, do you know what? No, we're going to change our function here a little. Let's make it be a little more extreme. I want it to go like that. Okay, so let's get rid of those. Let's get rid of... There we go. Okay, so our function's going to be a little more extreme. Okay, so the idea is that you get a trapezoid by connecting these two right here. So remember that trapezoid has a pair of parallel sides. So you get this one and this one, right? And then this is, the two on the edges are not parallel. Right? So the vertical lines are parallel. So then you're going to get another trapezoid that looks like this. And then you get another trapezoid that looks like that. Okay, so does everyone see our 3 trapezoids? Okay, so that first trapezoid, I'm going to like draw it here off on the side. It looks something like this. Now remember that this is x0 right here and this is x1. So the height is f of x0 and f of x1, right? And then how wide is it going to be? Delta x. Now if you remember that the area of a trapezoid is 1/2 of the... Now normally trapezoids are drawn like this. Right? Remember trapezoids are usually on their side, and you call this one base 1 and you call this one base 2, and then you have the altitudinal height. So remember it's 1/2 of base 1 plus base 2 times the height. Okay, now for us, f of x0 is your base 1, f of x1 is base 2, delta x is your height, correct? Because it's on its side. That's like one of the annoying things about this. So if I want the area of some trapezoid, which I'll call AI, that is going to be 1/2 f of x. Well, let's call this A1. The area of the first trapezoid will be f of x0, plus f of x1 times delta x. So just to give you an idea, the second you wanted to say rectangle. The second trapezoid will be 1/2 of f of x1 plus f of x2 times delta x. So notice for the first rectangle, the second number matches. For the second rectangle, the second number matches, right? So why am I doing this? So that you can figure out, well, the AI is going to be 1/2 f of xi minus 1 plus f of xi times delta x. That was like too hard to do for some reason. Okay. And actually, let's finish this up. Let's do A3 because you get the third one, right? Because we're only doing three trapezoids, not rectangles, trapezoids. Okay, sorry, I'm just like realizing like why do I'm stuck on rectangle. Like I keep on saying rectangle. So the last one is 1/2 of f of x2 plus f of x3 times delta x. So the total estimate will be a1 plus a2 plus a3, correct? Now I want to point something out. Do you see how you have f of x1 here and you have f of x1 here? You have f of x2 right here and you have f of x2 right here, right? You have pairs of those, but you only have one x0 and you only have one x3. So notice that this is n equals 3, right? Do you see how the last and the first term, there's only one of them? So when you add them together, a1 plus a2 plus a3, we can factor out the half from everything. Actually, the 1/2 delta x. And there's only going to be a single f of x0, but there's going to be two f of x1s, there's going to be two f of x2s, and there's only going to be a single f of x3. So notice this was the sum from I equals 1 to 3. And this actually gives you what we call the trapezoid approximation formula, which is Tn. If you are summing your n trapezoids, it's going to be the sum of those n trapezoids, so I have the sigma ai, is going to be 1/2 delta x f of x0, and then 2 for everything. And then the last one, the f of xn, will just be f of xn. So does it make sense? All these terms here will be doubled. Okay. Is everyone on board with that? So actually, I guess let me write a little more accurately here. What I really should put is that you're going to be doubled up to f of xn minus 1, and then the f of xn will not be doubled. Right? You double up to that last term, second to the last term, penultimate. Okay. So let's do an example. Interestingly enough, the trapezoid formula ends up being more accurate, because if it curves, see how like from here to here, the top of the trapezoid follows the curviness? So it stays as close as it can, basically, which makes it generally more accurate than the midpoint rule, but not always. And actually, there is a rule that you can use to figure out how accurate it will be, and I'm like looking at it right now. Right, yeah. Um, if it's really curvy, the trapezoid rule ends up being more accurate. If it like it follows it, but in some cases the midpoint rule is more accurate. It's really hard to say. There's actually what for people who study this, they spend a bunch of time like investigating like which curves should you use which sort of numerical integration method for and will be more likely to give a smaller error. And there's a whole study of this called numerical analysis. If you go and you look at like a CS department or a math department or an applied math department, they usually have like an undergraduate class called numerical analysis and a graduate level class, and it's just about studying all these algorithms to do numerical integration, numerical derivation, and a bunch of stuff like that. And they actually prove theorems like if you have this sort of function, which one will work better? And that's like all they do. I actually found that it was a really interesting class. I took it a long, long time ago. Applied mathematics is this, basically. Yeah, it's this like on steroids. So like if you ever want to take a class about AI, like especially neural networks, like there's a lot of integration and derivation that has to happen, and optimization, and they use a bunch of stuff like this to figure things out, like to make your neural network or to make your machine learning algorithm. It's basically just applied math. Like I would say that machine learning, neural networks, all that, it's applied math plus some statistics plus some computer science. Like you need a bit of each to do everything. Which is why most people are really bad at it, because like they usually know one area and they aren't like well-rounded in all of them. Like there's a lot of computer scientists, they don't know a lot of like the numerical analysis behind like why the algorithms work. Or you'll find a mathematician who knows like why the algorithms work, but they don't really know much about how to code. Or you'll find a statistician who like knows all the statistics, but then they don't know like the numerical analysis or like the coding to actually make it happen. So that's why like these data science degrees are becoming really popular. It's just like it's basically a applied math degree, statistics degree, and computer science degree all sort of wedged together. Like you're getting a minor in each of them, and all together that's like better than having one of them by itself in terms of like getting a job, basically. So I highly recommend it to people who want to make money. There seems to be like it's booming. All right, so let's do what's it called? An estimation. So we are going to let's do a cool function. Okay, so example, estimate using the trapezoidal rule with 12 for the definite integral. So does it make sense? T underscore n, right, is the trapezoidal rule. And our integral will be definite integral 0 to 1 e to the x squared, which I think you might be able to solve using integration by parts. I think so. But either way, it'd be like a double usage at least, right? Because that x squared, you'd have to probably do the integral. You'd set that as your u, and then that would become your du, right? But then like you'd have an x left over there, and then you'd have to do an integration by parts on that, and then with your x being your u, you'd get a du, and that would go away. So you probably have to do integration by parts twice to do this. So you're like, whatever, screw it. Like we're just gonna do it numerically. So your f of x is going to be e to the x squared. Your delta x is going to be b minus a over n, which is 1 minus 0 over n, which is 1 over n. Okay, your xi is going to be 0 plus delta x, which is 1 over n times I, so I over n. So this is not that bad. Xi equals I over n. Okay, so what's the formula? It's 1/2 of delta x times f of x0 plus 2f of x1 plus ... 2f of xn minus 1 plus f of xn. You notice Wolfram lends itself to doing this, right? Because you don't want to, like, you're going to have to plug all this in. You're going to do 1/2 of delta x, and you're going to have to do f of x1 plus 2 times f of x2. Oops, can't write. Plus 2 times f of x3 plus ... because I don't want to write them all. 2 times f of... Actually, let's not do t12. It's just too many. Let's make this a smaller number. I'm like... Yeah, we'll make it 5. So, because I already have like that written, basically. So I head up to x3. So then we'll have 2 f of x4 plus f of x5. Cool. So I've written it out. Like, I guess we could make the replacement that our delta x is what? I over n? Or I over 12, right? Or, sorry. Our delta x is 1 over n, which would be 1 over 12. There we go. And I guess really we should say that our xi is going to be I over 12. Yeah. Oh. We start with, let me actually look at the formula. We start with x0, my bad. I screwed that up here, huh? I like lost. Yeah, and I gotta change a couple things. Right. So let me move this stuff over. So plus 2 f of x1. Here's my f of x0. Okay, we gotta change our n to 5, so this should be I over 12 and 1/5 over here. There we go, thank you. Yeah, I hadn't really updated, huh? So xi is gonna be I over 5. Delta x is, let's just write that, delta x is 1/12. Right, so that's why you have the, 1/5, my bad. I'm stuck on that 12. Okay, that's why you got the 1/5, and then xi equals I over 5. Thank you. Okay, so plugging all this in is sort of a pain, and it's why Wolfram is sort of helpful. So let's change our screen over to Wolfram. Okay, so let's say quit again, have it restart. Okay, so what's our f of x? Our f of x is the exponent of x squared, right? If you type it in, you can see there it's e to the x squared. Oops. There we go. Cool. Now, we need to plug in some stuff. Our delta x is 1/12. Our xi is 0 plus delta x times I. Oh, damn, thank you. 1/5. Rerun. Okay, so your xi is I over 5. There we go. Which is why it's always good to check, right? You have it, like, spit it back out so you can, like, verify, like, yeah, that is what I actually wanted. Okay, now, what I highly recommend you do, because you're going to do f of x0 plus 2 times f of x1, 2 times f of x2, 2 times f of x3, 2 times f of x4, right? Then plus f of x5. What you can do is you can use the sum for your f of xi. So, and then we can do 2 times these. So which are the ones that actually need to be doubled? Yeah, right, so that's from 1 to 4, right? So do you see how instead of writing out 2 times f of x1, 2 times f of x2, 2 times f of x3, 2 times f of x4, you just do this. And then like, oh shit, look, it's there for you, right? Now, what else do you need to add to that? F of x 0. You also need to add to it f of x 5, right? Okay, then do you see how I have parentheses around it? What does that need to be multiplied by? 1/2 times. Oh, okay, I screwed up a parentheses. And then boom, look, there it is. It's 1/2 times delta x plus f of x 0, 2 times f of x1, 2 times f of x2, 2 times f of x3, 2 times f of x4, f of x5, boom! And then what you could do is you could just say, hey, turn that into a decimal for me. 1.48065. And you can compare this with what you get if you were just to have the function integrate from, what were we integrating between? 0 to 1? And apparently the actual answer is 1.4625, which is not that far off, right? We got 1.48 with stuff. You should have gotten 1.46 with stuff. That's pretty decent, right? For having, especially if you imagine if you were like 200 years ago, right? Trying to calculate this, like it'd be hard enough to add up all those numbers, right? Okay, so I highly recommend you use this trick that you only do this, you do the sum for those middle terms, so you don't have to write them all out. It really speeds up things. Okay, and that's like why this is way better than online calculators. For an online calculator, you'd have to plug in the whole thing, right? Like 1/2 times delta x times f of x0 plus 2 times f of x1 plus 2 times, right? You'd have to like literally write all that out. Like, because those middle terms are just the sums of the doubles, you can just write sum of the double and say the middle terms. Okay.